Hello, and welcome. Today, we're embarking on a journey into the world of polymers. This is a topic that is quite literally all around us, and even inside of us. Our overview will be based on the work of Professor Ricoberto C. Advincula in macromolecular science and engineering.
Let's begin by looking at the world of polymers. When you look at these images, you see a vast array of objects that are part of our daily lives. Storage crates, bottles, clothing, packaging materials, paints, and even bio-based materials like corn. On the other hand, you also see the environmental challenge they represent, with landfills filled with plastic waste. All of these things, the useful, the essential, and the problematic, are made of polymers. The term plastic itself gives us a clue about one of their most important properties.
The word plastics is derived from the Greek word plastikos, which means to mold or to shape. This term is often used as a catch-all for the entire class of polymer materials. More scientifically, we refer to this range of materials simply as polymers, or as chemists might call them, macromolecules, which literally means large molecules. A key theme throughout our discussion will be their life cycle. Recyclability, not just biodegradability, is a critical factor in how we manage these materials. And it's important to remember that polymers are truly everywhere, including in the biological systems that make up our own bodies, like DNA and proteins. To understand polymers, we need to place them in a hierarchy of matter. The diagram on the left shows us this dimensional hierarchy of organizational complexity. At the very bottom, on the scale of less than an angstrom, we have the fundamental particles, protons, neutrons, and electrons, which form atoms like hydrogen, carbon, and nitrogen. As we move up in scale to 1 to 5 angstroms, these atoms form simple molecules like water or methane. The next level, from 5 to 10 angstroms, includes what are called subnanoscopic molecules. Moving up again, between 10 and 150 angstroms, we find nanoscopic molecules, such as fullerenes or buckyballs. Finally, when we reach the scale of 100 to over 1,000 angstroms, we enter the realm of traditional macromolecules. This is where polymers live. Here we see simple linear polymer chains, randomly branched polymers, highly structured dendrimers, and interconnected polymer networks. This immense scale is what gives polymers their unique properties. Now let's consider the states of matter. For small molecules, we're familiar with the transitions between gas, liquid, and solid crystalline states. A graph of volume versus temperature shows a sharp first-order transition at the melting point, where a crystalline solid becomes a liquid. Polymers, however, behave differently. Due to the immense size and entanglement of their long chains, they do not have a gaseous state. They will decompose from heat before they can ever vaporize. Instead, their liquid state is a highly viscous, viscoelastic melt. From this melt, several things can happen upon cooling. If cooled slowly, parts of the polymer chains may align into ordered crystalline regions, resulting in a semi-crystalline solid. If we cool the melt and simultaneously introduce crosslinks, chemical bonds between the chains, we form an elastomer, or a rubbery material. If we cool the melt too quickly for crystals to form, the entangled chains get locked in a disordered solid state, creating what is known as a glass. This complex behavior, moving between viscoelastic melts, semi-solids, and glassy states, is fundamental to polymer science.
So, what is it that makes polymers so unique and important? They are a truly interdisciplinary field, of great interest to chemists, physicists, and engineers, and they have a massive impact on science and society. Their synthesis and modification draw on all fields of chemistry, from organic and physical to analytical and inorganic. While an organic chemist can often transition into polymer science, the reverse is not always as straightforward, because polymer science involves unique concepts like chain statistics, entanglement physics, and viscoelasticity that go beyond traditional small molecule chemistry. Industrially, polymers represent the largest sector of the chemical industry, primarily derived from the polymerization of petroleum feedstocks. They are often described as soft materials, which complements the study of hard materials like ceramics and metals in material science. While polymer is the scientific term, plastic remains the more popular and commonly used word, and it bears repeating. Almost everything, including biological life, is made up of polymers, both natural and synthetic.
Let's establish a more formal definition. A polymer is a large molecule, a macromolecule, comprised of repeating structural units called monomers, which are joined together by covalent bonds. The name itself comes from Greek, poly meaning many, and mer meaning parts. The monomer is the fundamental repeat unit. It's a small molecule with a specific chemical structure that allows it to react and link together in a series of steps to form the long polymer chain.
To form a chain, a monomer must have a minimum functionality of 2, which is often denoted as F equals 2. This means it must have at least 2 reactive sites to bond with 2 other monomers, allowing the chain to grow. We can see 2 examples here: styrene with its reactive double bond, and an amino acid with 2 different functional groups, an amine and a carboxylic acid at its ends. Both have a functionality of 2.
Arbitrarily, a molecule is often considered a polymer when it has at least 100 repeating units, as this is typically where we see the emergence of unique polymeric properties. Shorter chains, with perhaps 10 or fewer monomer units, are called oligomers. These can be thought of as very low molecular weight polymers. Sometimes, oligomers are designed to be telechellic, meaning they have reactive groups at their ends, allowing them to be linked together later to form longer chains. The process of creating these polymers is called polymerization. This is a chemical reaction that can proceed through various mechanisms common in organic chemistry, such as those involving radicals, cations, or anions, or through equilibrium reactions that release a small byproduct like water. To understand the structure and notation of polymers, let's consider a simple homologous series from organic chemistry: methane, ethane, propane, and so on. As you keep adding CH2 groups to the series, you are essentially creating a polymer called polymethylene. A long chain would be written as CH3, CH2, CH2, and so on, ending with a CH3 group. For simplicity, we use shorthand notation. We can write it as CH3-CH2-N-CH3, or even more simply as -CH2-N, where the N is a subscript representing the number of repeat units, also known as the degree of polymerization. Because polymerization is a statistical process, not all chains in a sample will have the exact same length. Therefore, we talk about the average molecular weight. There are different ways to calculate this average. The number average molecular weight, or MN, gives equal weight to every chain, regardless of its size. The weight average molecular weight, or MW, gives more weight to heavier chains. The ratio of MW to MN is called the polydispersity index, or PDI, and it gives us a measure of how broad the distribution of chain lengths is in a sample. The entire field of polymer science and engineering can be understood through the relationship between 4 key pillars. This is often visualized as a tetrahedron, connecting composition, molecular characterization, properties, and processing. First is composition and synthesis. This deals with the chemistry, the synthetic methods used, the target molecular weight and its distribution, the stereoregularity or spatial arrangement of the atoms, and the composition if it's a copolymer made from multiple monomers. Second, based on the composition, we have molecular and macromolecular behavior. This involves characterizing the polymer, how it behaves in solution, its thermodynamic properties, and its morphology, how the chains arrange themselves in the solid state, whether they are amorphous or form crystalline structures. Third, these characteristics determine the final material properties. These are the macroscopic qualities we care about for an application, such as mechanical properties like modulus and tensile strength, or electrical properties like the dielectric constant. Finally, all of this is linked to processing. This refers to how we shape the polymer into a useful object. The processing method, thermal history, and environmental exposure during manufacturing all have a profound impact on the final properties of the material. These 4 pillars are deeply interconnected. A change in one will affect all the others. Let's define a few more key terms. The repeat unit, as we've said, is the basic building block. It's important to note that this refers to the structure of the original monomer, not necessarily the simplest possible repeating chemical formula in the chain. For example, polyethylene is made from the monomer ethylene, even though the repeating structure is just CH2-CH2. At the very ends of a polymer chain are the end groups. These are structural units that terminate the chain. In some cases, as with telechellic polymers, these end groups are intentionally designed to be reactive for further chemical modification. The polymer backbone is the main chain or spine of the polymer. Other chemical groups, called pendant groups, may be attached to this backbone. The degree of polymerization, or dP, is the total number of repeat units in a chain and is directly related to the molecular weight. Since we're usually dealing with a distribution of chain lengths, the dP is also an average value. Polydispersity, as we mentioned, describes the degree of variation in chain lengths within a polymer sample. And finally, a polymer blend is a physical mixture of two or more different polymers, unlike a copolymer where different monomers are chemically bonded together in the same chain.
Now we can begin classifying polymers. One of the most fundamental classifications is based on the monomer composition. The simplest case is a homopolymer, which is prepared from a single type of monomer. An example is polystyrene, where the chain is just a long sequence of repeating styrene units, which we can represent as AAAAA. The diagram shows several ways to represent this linear polystyrene chain. You can see the full chemical structure, or a shorthand bracketed notation. We also see the polymerization of ethylene into polyethylene, where N molecules of ethylene link up to form a macromolecule. When a polymer is made from two or more different types of monomers, it's called a copolymer. There are several ways these different monomers, let's call them A and B, can be arranged along the chain, leading to different types of copolymers. If the monomers alternate in a perfectly regular fashion, like AB, 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 we have an alternating copolymer. If long sequences of A monomers are connected to long sequences of B monomers, like a long chain of A's followed by a long chain of B's, we have a block copolymer. If the A and B monomers are distributed randomly along the chain with no discernible pattern, it's a random copolymer. Finally, if we take a backbone made entirely of A monomers and attach branches made entirely of B monomers, we have a graft copolymer.
So, to formally define copolymers, they are a covalent mixture of two or more monomer types within the same polymer chain. It's crucial to distinguish this from a blend, which is just a physical mixture of separate polymer chains. The different arrangements we just saw, alternating, random, block, and graft, give rise to vastly different material properties, even if the overall chemical composition is the same. For example, the properties of a random copolymer are often an average of the two parent homopolymers, while a block copolymer can exhibit properties of both parent polymers simultaneously because the different blocks can separate into distinct domains. The specific sequence is controlled by factors like the reactivity ratios of the monomers during polymerization. Beyond composition, we can also classify polymers based on their chain architecture or topology. The simplest architecture is linear, where there is no branching along the backbone. Next is a random branched polymer. Here, branches emerge from the main chain. This branching can be a result of side reactions during polymerization, or it can be intentional, for instance in graft polycommoners. However, a branched polymer is not necessarily a graft polycommoner. Branching can occur with just one type of monomer. We can also have designed branched polymers, where the branching is highly controlled. Star polymers have multiple polymer chains or arms emanating from a central core. Cone polymers have a linear backbone with many pendant polymer chains attached along its length, like the teeth of a comb. These are often synthesized using special techniques, involving macroinitiators or macromonomers, which are themselves short, pre-made polymer chains with a reactive group.
Another important architecture is a network. This is formed when linear or branched polymers are joined together by crosslinks, which are covalent or ionic bonds connecting different chains. This creates a single, giant molecule. The process of forming a network leads to significant changes in properties, transforming a processable thermoplastic material into a thermosetting material that will not melt. Vulcanization of rubber is a classic example of creating a network. Ladder polymers consist of recurring fused ring structures, creating a rigid, double-stranded backbone. Semi-ladder polymers have sections of these fused rings interspersed with more flexible, open chain units. Supramolecular assemblies are structures where molecules are linked not by strong covalent bonds, but by weaker, non-covalent interactions, like hydrogen bonds or van der Waals forces. These are common in nature, for example in the structure of DNA. Finally, we have highly branched architectures like dendrimers and hyperbranched polymers. Dendrimers have a perfectly regular tree-like branching structure that emanates from a central core. This precise generation-by-generation synthesis results in macromolecules that are essentially monodisperse. All the molecules have the same size and structure. Hyperbranched polymers are also extremely branched, but lack the perfect regularity of dendrimers. Their branches are more randomly distributed.
Let's look more closely at some of these architectures. To create linear polymers from monomers like AA and BB, where each monomer is difunctional, they simply link end to end.
To create a network or a hyperbranch structure, we need at least one monomer with a functionality greater than 2, such as the AB2 monomer shown, which has 3 reactive sites. The image of the dendrimer shows this perfect layered branching from a central point. Network formation is visualized as taking individual linear polymer chains and linking them together with crosslinks, creating a tangled, interconnected web. This is what happens in ionomers, where polar ionic groups along the nonpolar backbones cluster together, acting as physical crosslinks. Some polymers can also form liquid crystalline phases. These are mesophases, states of matter that are intermediate between the perfect order of a crystalline solid and the complete disorder of a liquid. In these phases, the polymer chains have some degree of orientational or positional order. The nematic phase, for example, has the chains aligned in a common direction, but with no positional order, while smectic phases have the chains aligned and also arranged in layers.
A major way to classify polymers is based on the process used to create them. The historical classification, proposed by Carruthers in the 1930s, divides polymerization into 2 types, addition and condensation. Addition polymerization was traditionally defined as the process where you break a double bond in the monomer to link them together. The key feature is that the repeating unit of the polymer contains the exact same atoms as the original monomer. Condensation polymerization, on the other hand, was defined as a reaction where linking monomers together results in the elimination of a small byproduct molecule, such as water or methanol. This means the polymer repeat unit has fewer atoms than the monomers it was made from. However, this classification has its limitations. For example, some polymerizations proceed by opening a ring structure. No byproduct is lost, so it's not a condensation reaction, but no double bond is broken, so it doesn't fit the classic definition of an addition reaction either.
This leads us to a more modern and mechanistic classification: chain growth versus step growth polymerization. This focuses on how the polymer chain actually grows. Step reaction, or step growth polymerization, is a process where polymers are built in a stepwise fashion. Monomers react to form dimers. Dimers can react with monomers to form trimers. 2 dimers can form a tetramer, and so on. Any 2 molecular species in the reaction mixture can react with each other. A key characteristic is that the monomers are consumed very early in the reaction, but the molecular weight of the polymer only starts to rise significantly at very late stages, when these short oligomer chains start linking together. Chain reaction, or chain growth polymerization, is different. Here, an initiator molecule creates a reactive center on a monomer. This active center then rapidly adds more and more monomer molecules one at a time to the end of the growing chain. The molecular weight increases very quickly. In this process, the reaction mixture contains a high concentration of unreacted monomer, a very small number of actively growing chains, and the already formed high molecular weight polymer. It is important to note that polymers with identical repeat units can sometimes be formed by different mechanisms, which can lead to different properties due to variations in molecular weight, end groups, or chain branching. Let's summarize the key features of chain reaction growth. It's often initiated by free radicals, which are created from molecules like peroxides that break apart with heat or light. The process has 3 distinct phases: initiation, where the active center is formed; propagation, the rapid growth of the polymer chain; and termination, where the growth is halted, for example by 2 radicals combining. High molecular weight polymer is formed almost immediately, and it remains steady throughout the reaction. As the reaction proceeds, the monomer concentration steadily decreases. Longer reaction times increase the yield of the polymer, but not necessarily its molecular weight, unless it's a special type of living polymerization, where termination is absent. The graph of polymerization rate versus time shows different possibilities. In curve A, the rate is constant. In curve B, the rate decays over time as the initiator is consumed. In curve C, the rate decays to a constant value. Now for step growth. This process usually involves a succession of condensation reactions. As mentioned, any 2 species can react. The molecular weight rises steadily throughout the reaction, but a dramatic increase to high molecular weight only occurs at very high conversions of the functional groups. The graph shows this relationship based on the Carruthers equation. The degree of polymerization, dP, is equal to 1 divided by 1 minus p, where p is the conversion. You can see that to get a high dP, the conversion p must be very close to 1, meaning the reaction must go almost to completion. Examples of step growth polymers include polyesters and polyamides like nylon. There are still other ways to classify polymers. We can classify them by their origin. Synthetic organic polymers are synthesized from petroleum-derived products. Biopolymers are derived from natural sources, such as proteins, polysaccharides like cellulose, and natural rubber. Semi-synthetic polymers are made by chemically modifying natural polymers. Then there are inorganic polymers, which have a backbone that is not based on carbon. Examples include siloxanes, silicon-oxygen backbones, silanes, and phosphazines. Organometallic polymers contain both inorganic and organic components in their monomer unit.
Another crucial classification is by chain configuration. This requires looking at the stereochemistry of the polymer chain. First is monomer orientation. In most vinyl polymers, the monomers add an irregular head-to-tail fashion. A head-to-head arrangement is also possible, but usually less common. Then we have stereoisomerism, or tacticity. This applies to polymers with a pendant group, like the X group shown. If all the pendant groups are on the same side of the polymer backbone, it's called isotactic. If the pendant groups alternate regularly from one side to the other, it's syndiotactic. If the pendant groups are arranged randomly, it's atactic. Tacticity has a huge impact on properties. The regular structures of isotactic and syndiotactic polymers allow the chains to pack closely together into crystalline regions, resulting in stronger, more rigid materials. The random atactic structure prevents this packing, leading to an amorphous, often softer material. We can also classify polymers by their thermal behavior. Thermoplastics are materials that become soft and fluid-like upon heating, allowing them to be molded into desired shapes, which then become stable upon cooling. This process is reversible. Most thermoplastics are made of linear or branched polymers. Thermosets, in contrast, are formed from an initial mixture of reactive, low molecular weight compounds that react upon heating in a mold to form an insoluble and infusible network. Once this cross-linked network is formed, or cured, the material can no longer be melted or reshaped. The only way to alter its shape is by machining it. Physical performance provides another set of classifications. Polymers that can stretch significantly and then rebound are called rubbers or elastomers. Plastics, adhesives, and fibers are other categories based on their primary application and mechanical properties. A term you might hear is resin, which is a generic term for a polymer, but often implies a thermoset material. The ability of a polymer to crystallize is a key property. Crystallinity is promoted by factors that allow the chains to pack in an orderly fashion. This includes highly stereoregular structures, isotactic or syndotactic, linear chains with little or no branching, and the presence of highly polar groups that can form strong intermolecular interactions, like the hydrogen bonds between polyamide chains shown in the diagram. We can classify polymers by their end-use application. The major categories are plastics, fibers, elastomers, coatings, and adhesives. We can also classify them based on their morphology, or their degree of solid-state order. A polymer can be highly crystalline, semi-crystalline, containing both crystalline and amorphous regions, or completely amorphous, meaning the chains are tangled in a completely disordered arrangement. The graph of stress versus strain reveals the mechanical behavior of these different types. A brittle plastic breaks at low strain. A tough fiber can withstand high stress. A plastic with yield can deform before breaking, and an elastomer can undergo very large strains and still return to its original shape. The images on the right show models of how polymer chains fold and organize to form these crystalline regions, or lamellae, within a semi-crystalline material.
Let's briefly touch upon the history of polymers. The word polymer was first used by the Swedish chemist Berzelius in 1833. Natural polymers were in use for centuries, but the 1840s saw a key development with Charles Goodyear's invention of vulcanization, which turned sticky natural rubber into a useful, durable material. By the 1860s, some synthetic polymers had been reported, but their macromolecular nature was not understood. The first truly synthetic polymer, Bakelite, was invented by Leo Baekeland in the early 1900s. Still, the concept of polymers was poorly understood, often confused with colloidal science.
The breakthrough came in the 1930s with Hermann Staudinger, who introduced the concept of macromolecules as long, covalently bonded chains, for which he won the Nobel Prize in 1953. Around the same time, Wallace Carothers at DuPont commercialized neoprene rubber and nylon fibers. World War II spurred a massive expansion of polymer research, especially in the US, as a substitute for natural rubber. The 1950s brought another revolution with Carl Ziegler and Giulio Natta, who developed catalysts for coordination polymerization, allowing for the synthesis of stereoregular polymers like isotactic polypropylene. This gave unprecedented control over polymer structure and led to materials with superior properties. In the 1960s, Paul Flory laid the theoretical foundations for polymer physics, providing a quantitative basis for understanding their properties. More recent Nobel Prizes have recognized advances like Bruce Merrifield's work on solid phase synthesis, P.G. de Genz's theories on polymer physics, the discovery of conducting polymers by MacDiarmid, Heeger, and Shirakawa, and the invention of olefin metathesis polymerization by Grubbs, Schrock, and Chauvin.
This history can be summarized by looking at the evolution of synthetic macromolecular architectures. In the 1930s, scientists could primarily make linear polymers, like flexible coils and rigid rods. The 1940s brought the ability to make cross-linked networks. By the 1960s, there was more control over branching, leading to star-branched and comb-branched architectures. And from the 1980s onwards, highly sophisticated dendritic architectures, like dendrimers, became possible. The overarching theme is one of increasing control over polymerization and topology.
Bakelite, the first commercially synthetic polymer resin, is still used today. It's a thermoset made from the reaction of phenol and formaldehyde, which forms a heavily cross-linked rigid network solid. Of course, nature is the master of polymer synthesis. Natural polymers include polysaccharides like cellulose, which is made of repeating glucose units. Proteins are polyamides of alpha amino acids, and polynucleotides, like DNA, are polyesters of phosphoric acid and nucleosides, forming the iconic double helix structure that carries our genetic code.
Other important natural polymers include lignin, which acts as the cement holding cellulose fibrils together in wood. Lignin's complex structure is related to humus and coal. Asphaltenes are used as binders in road construction. Rubbers, in their natural form, are polyterpenes, specifically poly-1,4-isoprene.
Now let's consider polymer blends, which are physical mixtures of different polymers. The rationale for creating blends is often economic. It can be cheaper to blend existing commodity polymers to achieve desired properties than to develop and synthesize a completely new polymer. A blend can be miscible, meaning the two polymers mix at the molecular level to form a single phase, or immiscible, where the two polymers do not mix well and separate into distinct phases. The properties of a blend can be synergistic, better than either component, additive, an average of the components, or non-synergistic, worse than the components. Most polymer pairs are immiscible, resulting in a phase-separated morphology.
This brings us back to copolymers, where different monomers are covalently linked. We've discussed the main types: alternating, random, block, and graft.
Block copolymers are particularly interesting. They are composed of long sequences, or blocks, of one monomer type covalently bonded to blocks of another type. Because the different blocks are often chemically incompatible, like oil and water, they try to separate from each other. However, since they are covalently linked in the same chain, they cannot separate on a macroscopic scale. Instead, they undergo microphase separation, self-assembling into highly ordered nanostructures. The specific structure that forms, spheres, cylinders, gyroids, or lamellae, depends on the relative lengths of the different blocks and the strength of their repulsion. The phase diagram shows how these different equilibrium mesophases are formed as a function of the volume fraction of one block and the segregation strength, which is a product of the Flory interaction parameter and the degree of polymerization. This self-assembly is a powerful tool for creating materials with precisely controlled nanostructures. The principle of hierarchical self-assembly is not limited to synthetic block copolymers. It's a fundamental concept in nature. DNA, enzymes, viruses, and bacteriophages are all examples of complex functional structures built through the hierarchical assembly of simpler polymeric building blocks. Even complex topological structures, like molecular knots, can now be synthesized. This progression from simple building blocks like oligomers and polymers to complex multi-level hierarchical structures is a major frontier in material science. Let's briefly cover the nomenclature of polymers. The simplest source-based naming method is to use the prefix poly followed by the name of the monomer in parentheses. For example, the polymer made from styrene is called polystyrene. The polymer made from vinyl chloride is polyvinyl chloride, or PVC. IUPAC has a more systematic, structure-based nomenclature. This involves identifying the smallest constitutional repeating unit, CRU, and naming it according to standard organic chemistry rules. For copolymers, infixes are used to denote the arrangement of monomers. -CO for an unspecified or random copolymer, -ALT for alternating, -block for block, and -GRAFT for graft. The tables here show the structure-based, source-based, and common trivial names for a variety of widely used polymers like PVC, PMMA, PET, and polystyrene. On an industrial scale, we can divide plastics into two broad categories. First are commodity plastics. These are produced in huge volumes at a very low cost, typically 20 to 40 cents per pound. Their properties are sufficient for everyday applications, but are limited by relatively weak intermolecular forces. The big five commodity plastics are low-density polyethylene, LDPE, high-density polyethylene, HCPE, polypropylene, PP, polyvinyl chloride, PVC, and polystyrene, SP. The other category is engineering plastics. These are produced in lower volumes but have superior mechanical and thermal properties, making them suitable for more demanding applications, like parts in automobiles or electronics. They are higher cost but offer higher performance. The pyramid diagram illustrates this hierarchy, from standard commodity plastics at the base through engineering plastics to high-performance and advanced materials at the very top. These higher-tier polymers are often more crystalline, have stronger intermolecular forces like hydrogen bonds, or contain highly aromatic rigid backbones. Beyond plastics, polymers are used as fibers, rubbers, or elastomers, coatings like paint, and adhesives. Managing the life cycle of all these materials is a major challenge, leading to the field of recycling. This involves collecting and separating plastic waste, followed by either mechanical recycling, melting and reforming, or chemical recycling, which involves depolymerization back to monomers, which can then be purified and repolymerized to create virgin quality polymer. To create finished products, raw polymer is subjected to various formative manufacturing processes. Plastic extrusion involves pushing molten polymer through a die to create a continuous profile, like a pipe or a film. Injection molding involves injecting molten polymer into a mold cavity to create complex three-dimensional parts. Compression molding involves squeezing a polymer charge in a heated mold. Other processes include thermoforming, reaction injection molding for thermosets, and fiber spinning to produce filaments. A more recent development is 3D printing, or additive manufacturing. Unlike traditional subtractive manufacturing, where you cut material away from a larger block, additive manufacturing builds up an object layer by layer from a digital 3D CAD file. This process has several advantages. It creates less material waste, can produce highly complex structures, and is ideal for rapid prototyping and limited production runs. A wide range of polymers, including polyesters, polyolefins, and polyurethanes, are now available for 3D printing. The challenge of plastic waste has led to new ways of thinking about recycling. The goal is moving beyond simple recycling to upcycling. Catalyst-driven upcycling aims to take discarded polymer waste and, through chemical reactions, convert it not just back into its original monomers, but into new, higher-value chemicals and materials. The diagram shows how waste polymers could be catalytically converted into fuels or valuable chemical feedstocks that can then be used to make new high-performance materials. This transforms waste from a problem into a resource.
Looking to the future, the field of polymer science is being transformed by artificial intelligence and machine learning, or AI/ML. These computational tools can accelerate the discovery and design of new materials. Machine learning algorithms can be trained on existing data to predict the properties of a new, hypothetical polymer based on its structure. This allows scientists to screen thousands of potential candidates virtually before ever stepping into a lab. This can be taken a step further with autonomous or self-driving laboratories. The workflow shows a system where AI designs a synthesis route, a robotic platform carries out the chemical synthesis, and inline characterization tools analyze the product. The results are fed back to the AI, which learns from the experiment and then designs the next improved iteration. This closed-loop cycle of design, synthesis, and analysis, driven by machine learning, has the potential to dramatically speed up the discovery of new polymers with tailored properties. AI and data analytics can help us uncover new structure-property relationships and design better formulations faster than ever before. This concludes our overview of the vast and fascinating world of polymers, from their fundamental definitions and classifications to their history, industrial production, and the future of their design. Polymers continue to be a cornerstone of modern material science and engineering.
Thank you.